In this problem, we're asked to find the angle that maximizes the volume of a cylinder that's been inscribed in a sphere of radius A, as shown in this picture. So we draw the sphere, and we pick some angle from, say, due north, and we draw a rectangle, or a cylinder that goes with that. That would end up looking something like the following. So it looks something like this. And as we increase the angle, the cylinder gets wider and we have more volume, but eventually it reaches some point where it's maximized, and then it gets smaller again, and we want to find the angle that does that. Having already solved the problem, the angle is marked there in red, and we can see that that's going to be the case that gives us the biggest inside of that cylinder. So now the volume of a cylinder is pretty well known to be, the volume is pi, because there's always a pi, times r squared times h. That is, we find the area of the circular cap, and when we stretch it a distance h out. So this formula has been well known for a very long time, and we're going to use this. The problem we have, of course, is that we don't have either r or h as our free variable. We want it to be instead theta. So we're going to have to figure out r and h in terms of theta. Luckily, getting r and h as a function of theta will be easy, because basically we've described a right triangle. And then we have that the radius of the sphere A is our hypotenuse, and the radius of the cylinder r is one leg. The other leg, we have to go over here and say, well, this is the leg we want, but this is the height of the cylinder due to the symmetry of the cylinder, so our leg is clearly h over 2. And finally, of course, we define our angle as the angle from the North Pole, which in this case is theta and is drawn there. So moving forward, we just use right triangle trig to connect these, and rather than spend a lot of time worrying about the trig functions, I'm just going to figure them out on the fly. So I'm going to say sine of theta is definitely going to be the opposite side, which is r, divided by the hypotenuse, which was a. And cosine of theta is going to be just the adjacent side, which is h over 2, over the hypotenuse, which is a. And this allows us to then combine these up and say that, oh, well, then r has to be a sine theta, and h has to be 2 cosine of theta, and of course the scale factor of a in front. So there we have it. Now we recall that our volume that we wanted was pi r square h, so it's going to be pi times the square of a sine theta times simply 2a cos theta. Which can certainly be cleaned up and maybe made less multicolor as pi 2 pi a cubed sine of theta squared cosine of theta. That's the function that we're going to eventually want to optimize. To do our optimization, eventually we're going to want to take dv d theta. So we go over here and we say the things in orange are just a constant and they just come out front, 2 pi a cubed. And now I'm taking the derivative of what is essentially a product, this times that. So we're going to get the derivative of the first times the second, plus the first times the derivative of the second. The derivative of the first is now an extended chain rule, so we're going to pick up something like 2 sine theta, that's dd theta of that, but then we need to take the derivative of the sine, and so we pick up a cosine theta. But it is already times a cosine theta, that's this guy. And then we're going to add in the first one, which was sine squared of theta, times the derivative of cosine of theta, which is minus the sine of theta. So we end up with something that looks like that. Cleaning this up just a little bit, we have our constant just coming along out on the outside as always, and now we'll have two terms that are 2 sine theta cosine squared theta minus sine cubed theta. And those are our two terms from the product rule. We know that to get the optimal value, we're going to force dv d theta to be 0 and see what theta comes out. So we're going to take that derivative and make it 0. This is our derivative, and we're going to make it 0. It's really not that nice. We can certainly divide out the constant, so we might as well do that, and we'll just have 2 sine theta cosine squared theta minus sine cubed theta equals 0. But this is the thing that looks disturbingly transcendental since it's a mixture of trig functions. But we can do some cleverness. It usually helps to factor things out, so we'll pull out sine of theta times something else. And we have on the inside 2 cosine squared theta minus sine squared theta. And of course still equal to 0. That's an improvement because I've got two factors, and we'll be able to use the factor theorem later. But one of those factors is still not particularly pretty. What I have in here is now the two factors are either sine of theta is 0 or 2 cosine squared theta minus sine squared theta is 0. Because the factor theorem says if two things multiply to 0, one of them must be 0. The first one has only one solution in the physically meaningful range, because we know that theta has to be between 0 degrees and 90 degrees, and the only time in that case that sine of theta is 0 happens when theta is 0 degrees. And we can see that that's not going to be our maximum area because that's going to have a volume of 0, so we don't have to really worry about that one. But then we have the thing in blue, the 2 cosine squared theta minus sine squared theta equals 0, and that's just going to be more complicated because, again, equations involving multiple trig functions often end up having transcendental, that is, non-algebraic solutions. Happily, there's a little bit of a trick we can play here, because we can take our functions and we can play a little bit of trig games with them and say, hey, sine squared is really 1 minus cosine squared for any angle, and so we have that. And that we can clean up to being 3 cosine squared theta minus 1 equals 0. And that's going to be pretty easy to do because we can solve that and it's only one trig function. So 3 cosine squared theta equals 1, or cosine squared theta equals 1/3, or cosine theta equals 1 over root 3. I can neglect the minus 1 over root 3 solution because that would be in second or third quadrant, and we know that we only need to be in first quadrant. So cosine of theta equals 1 over the square root of 3, or theta is inverse cosine of 1 over root 3, and our handy dandy calculator will tell us that that is approximately 54.8 degrees, which will give us our maximum volume. It's pretty easy to render a quick graph of this in, say, Desmos, and we have it plotted on the left for all possible angles, although the only physically meaningful ones are between 0 and pi over 2, or 0 and 90. And just to remind you again, to illustrate, we start with no volume, and then we go up to this value, which is 54.8 degrees, and then we go back to no volume because the cylinder ended up having no height. So there we have it. There is an optimization problem pretty straightforwardly with just a little bit of trickery to it to show us where the maximum volume would be.